Now let's look at telescopes and how they developed after their initial invention by Lippershey and their initial use by Galileo. We get to the point of astronomy here because we have to remember that from antiquity through the ancient Greeks until the invention of the telescope in 1609, the information from the sky was extremely limited. All astronomy was positional. All that you could measure for any object in the sky were essentially three things: its position in terms of two angles, and its apparent brightness, how bright it appeared to be. Stars and even planets were too small and too far away to see their size. And without distance, there's no information on the true size, true brightness, true mass, for example, of any astronomical object. This is the idea of the celestial sphere, which is a natural convenience when we don't know the distance to anything. Imagine everything painted to a sphere that goes around the Earth. It's worth bearing in mind that it took 200 years after Copernicus to prove that the Earth was actually moving, and over 200 years after Galileo to measure the distance to any star. Let's look at angles in astronomy, because we move from the familiar realm of big angles to the realm of very small angles. And that's the source of some of the difficulties in observational astronomy, or in improving knowledge through this time. A circle is divided into 360 degrees. And to reference a degree is twice the angular size of the moon or the sun in the sky. Each degree is made up of 60 arc minutes. And we see here, zooming in on 1 degree, how small a single arc minute is. 1 arc minute is the angular resolution of the naked eye. That's the smallest angle on a clear night with a sharp, clear sky you could possibly see. Zooming in again on an arc minute, it's divided into 60 arc seconds. An arc second is obviously a tiny angle. An arc second is about the angular resolution of a main ground-based observatory, a 1 or 2 meter telescope on a good mountaintop observatory. That's the smallest angle you can readily see with a decent-sized telescope. When we look at angles in astronomy, we need some reference for these small angles. So let's just use the analogy of a soccer ball or a basketball. A 1 arc minute, the angular resolution of the naked eye, would be the angle subtended, or the angle made by either side, coming to the apex in your eye, of a soccer ball 800 meters away. Coming in by 80 meters, it would subtend about a degree. And at 8,000 meters, or 5 miles, it would subtend an arc second. Now we can see how small an arc second really is. Imagine trying to look at a soccer ball or a basketball 5 miles away and see its extent. Planets are large, 10,000 or more kilometers in diameter, and stars are enormous, millions of kilometers in size. But they are so far away that the angles they subtend in the sky are tiny. And so astronomers are stuck measuring small angles, and that's why astronomy progressed so slowly after the invention of the telescope. Again, for reference, the sun and the moon are 30 arc minutes, or half a degree. The eye will see or resolve about 1 arc minute, and Galileo's best telescope saw about 6 arc seconds, or 1/10 of an arc minute. We also have a tool for measuring size called the small angle formula. It's a simple result of trigonometry. But when the angle is small, we can relate the true size of something to the angular size it subtends at the eye and the distance. And here we see the linear size d equals the angular size alpha, measured in radians, times the distance, divided by 206,265. So if you put the distance in the same units, meters, kilometers, whatever you prefer, then you know two of these objects, two of these unknowns, you can get the third. So the small angle formula, you can see the ambiguity when you don't know distance. In example A in this diagram, an object that's 2 times bigger and 2 times further away appears to be the same size. It's obviously not the same kind of object. In example B, an object the same size 2 times further away has half the angular size. So you have to know the distance to an object or its true size to understand its place in the universe. The key is that in this equation, if you know any of the two quantities, you can get the third. We also measure brightness, and there's ambiguity here. Without other information, how bright something appears says very little about how intrinsically bright it is. So we have two examples. In example A, an intrinsically brighter object can appear dimmer than an intrinsically faint object when it's further away. So if you couldn't see what the objects were, the candle can be brighter than the fire at a larger distance. In example B, when both are at the same distance, the intrinsically bright object appears brighter than an intrinsically faint object. You can imagine a situation where, for example, a small light like a night light is close to you, a more luminous light like a light bulb is further away, and an even more luminous light source like a floodlight is even further away. And if their distances were arranged appropriately, they might appear to be equal brightness or even equal size, apparent size, but they're obviously hugely different objects. This is an example of the ambiguity based on distance, which is why we always need distance in astronomy. This is the key. We also have the idea of the inverse square law, which is the way the brightness of light changes with distance from an object that's emitting light in all directions. So for example, if we take a light bulb or a star, and we move the star or the light bulb 2 times further away, the number of photons or waves of light that pass through a given area goes down by a factor of 4. We move it 3 times further away, the number of photons or waves of light goes down by a factor of 9, and so on. It's the inverse square. In the upper right, we see this diagram how the light through a similar size square dilutes with distance, and that's the basis of the inverse square law of light. This, coincidentally, is the same way that gravity goes down with distance through space, and actually, as was realized later on in the 19th century, the strength of an electric or magnetic field. So it's quite a basic physics principle. Meanwhile, there was progress in telescope making from the time of Galileo, as various astronomers and optical engineers of the time developed ways to measure and build bigger telescopes. Remember that measuring distances to the sun and the planets or any stars meant measuring these very small angles, less than an arc minute. Remember also that the optics of the time were very crude. We've already talked about the aberrations of the early telescope using lenses, and how difficult it was to engineer lenses or grind lenses, for example, to a parabolic shape. The easiest lenses to make were spherical. So telescopes suffered from really bad aberration, both chromatic and spherical, and they were very frustrating for observers. It means it was also hard for people to repeat each other's observations, because everyone's telescope had different problems and different aberrations. The most direct way to minimize the effect of optical defects was to increase the focal length. As a practical matter, that was the easiest way to minimize these effects. That makes the angular deflection smaller, and so it increases the tolerance with which you can have an uneven surface. But the effect of this is to make the telescope longer and harder to point and keep collimated, so you end up with another problem. Christian Huygens is an important figure in this time, a major scientist and a contemporary of Newton, who built a 2.5-inch aperture, 12-foot focal length telescope. He had even larger later telescopes that were less successful. However, even with this telescope, he was able to discover Titan, moon of Saturn, and Saturn's rings in 1659. When we look at some of the telescopes of this time, the 17th century and into the 18th century, we can see what extraordinary creations they were. This telescope of Jacob Hevelius from Poland is 150 feet long. So you can see the business of getting a long focal length and small angle of deflection has made an incredible device which will obviously sag, which will obviously be subject to buffeting by the wind, and so it has another entire set of problems. Telescopes were simply not compact enough and wieldy enough to be used sensibly. Here are 2 more examples. Huygens' 210-foot aerial telescope, as it's called, and Cassini's 212-foot telescope at the Paris Observatory. These were curiosities, of course, at the time that attracted crowds, and scientists did their very best to get observations with them, but it was very difficult. A new technology was needed, And eventually that technology came around the time Newton was working. John Gregory invented the reflecting telescope. You can see here that by using a mirror, by reflecting light, so in this diagram on the right, the sky is coming on the left side, so the starlight is coming in from the left to the right. It's hitting a parabolic mirror, reflecting to a secondary mirror, and then bouncing off to a focus through the center. This folded design, using mirrors to reflect and parabolic surfaces rather than spherical surfaces, gives an upright image with two internal foci. It's difficult to fabricate a telescope like this because grinding a parabolic mirror is not easy. It's not really any easier than grinding a parabolic lens, but you end up with a real image before the eyepiece. And it solves a major problem of telescopes that use lenses. Since it's a basic optic principle that angle of light reflection is the same at all wavelengths, angle of incidence equals angle of reflection regardless of wavelength, these telescopes have no chromatic aberration, so that one problem is solved. Below that we see Newton's telescope from 1668. He invented a slightly simpler design, which had a parabolic primary and then a flat diagonal secondary, deflecting the image off to the sides, where you could put an eyepiece. The image quality was poorer than the Gregorian seen above, and because mostly it initially used spherical mirrors, because that was all Newton could create. Around 1672, Laurent Cassegrain, a Catholic priest who taught high school, invented a design that is still used in many cases today. Many of the large telescopes at Arizona use a Cassegrain design. It has a parabolic primary, a convex secondary mirror, and a very short tube. So the folded design makes the telescope very compact, and you have an inverted image that's at a focus through a hole in the primary. Now, cutting the hole in the primary loses you some of the light in collection, but it's a small fraction of the total collection area. It's a price worth paying. A major problem with this design and all the reflecting telescope designs was creating the reflective surface for the mirrors. Newton developed an alloy called speculum metal. And remember, Newton was an alchemist, so he was playing around with various materials trying to turn lead into gold, so he had a lot of experiments along this line to help his telescopes. His best composition involved about 2/3 copper, 1/3 tin, and a little bit of arsenic. His various experiments showed that if you put too much copper, you get too much reflection of red light, and if you put too much tin in, you get too much blue light. So to get a color balance and a uniform reflection of all the different waves of light, you have to play with the chemistry. These mirrors and the material he used to coat them is brittle, which means they were very difficult to cast. Also, the reflectance was not great. It only reflected just a little more than half of the incident light, and it tarnished or rusted very quickly. However, this speculum metal, invented by Newton, was used for almost 200 years until better alloys could be developed. Another innovation in the use of Galilean telescopes and the new reflecting telescopes was the use of micrometers in the eyepiece. Because remember, you're trying to measure sizes of things like planets, seen here, Mars on the lower right, and also separations between objects in the field of view, like stars, double stars, binary stars, a planet and its moons, for example. So to measure these small angles, which are small compared to the field of view, they will actually depend on where you place your eye and how you focus your eye. So you need a guide to the angles in the eyepiece, in the field of view. In the late 1630s, William Gascoigne noticed a spider web on his Keplerian telescope in the field of view, and he saw it was in focus. And it gave him the idea of putting screw-driven filaments at the inner focus and being able to adjust with a screw the filaments vertically and horizontally, essentially to measure a grid line in a well-calibrated way. From geometry of optics and the distance between filaments, you can determine the angular separation of the filaments. This is called a filar micrometer, and it enormously improved the accuracy of telescopic measurements at the time. And that's the end of this topic.